Today's lesson, we are going to look at something called oxidation numbers. Now, oxidation numbers are very, very important when we talk about chemical bonding, and it's actually going to lead into the next lesson, which has to do with how we actually write our chemical formulas. But knowing how oxidation numbers work will actually help us. So, just a little bit of review here. Ionic bonds, remember, are when we have two oppositely charged ions and they bond because of the electromagnetic force. Because if you think about it, opposites attract. So the negative and the positive will attract each other. So an ionic compound is made up of chemicals that are ions, that are ionically bonded to each other. So now let's take a little bit of a closer look at the composition here of that ionic compound. If we take a look at something that is ionic, and you guys know this already, this is from elements on the opposite ends of the periodic table. And if you remember, an ionic compound is made up of something that is a metal and something else that is a nonmetal. So let's look at those valence electrons. In general with metals, we have 1, 2, or 3 valence electrons that are very loosely held in their valence shell. Whereas the nonmetals have 6, 7, or 8, and sometimes even 5 electrons that are held very tightly. And these are held by what's called an effective nuclear charge. So this is the actual pulling force of those protons on those electrons. So, now this part may or may not be in your notes. I can't remember quite honestly. What happens is when these two atoms, one metal and one nonmetal, come together, the nonmetal actually grabs the electrons from the metal. And that's because, remember, they want to achieve stability, that magic number of 8. And so for the nonmetals, it's a lot easier for them to gain electrons than it is for them to lose. It's a numbers game. If you have 6, 7, or 8, it's a lot easier to gain 1, 2, or maybe 3 than it is to lose that many. On the metal side, it's a lot easier to give away those extra electrons than it is, 1, 2, or maybe even 3 electrons than it is to gain the 7 or 8 or 7, 6, or 5 that you might need to make the 8. So once we have these two ions, then they are actually then held together by that electromagnetic force. Alright, so that's kind of a little bit of review. But if you take a look at what this means in terms of oxidation number, the number of electrons an atom is willing to either gain or lose is called its oxidation number. So if we look at simply the tall columns on the periodic table, this takes out all of those transition metals, we actually get a pattern. Group 1 oxidation number tends to be a +1. Group 2's is a +2. Then we jump over to group 13 where we have a +3. The one group that's kind of split is group 14 because the elements at the top tend to act more like nonmetals, so they tend to be a -4 in the situation, whereas the ones towards the bottom like tin and lead tend to be that +4. You move over to group 15 with nitrogen. That's a -3 because they want to gain 3 in order to make 8. So they have 5, they want to gain 3, that gives them a -3 oxidation number. Oxygen's group tends to be a -2, and the entire halogens family is a -1. And so this means we can actually predict the oxidation numbers for certain elements. Now, we can do that with individual elements just like that, just like what we talked about on the periodic table. We can also take a look at things in a compound, and that's what we're going to do here. So if I take a look at elements in a compound, now they have to actually total up to be 0. So let's take a look at a compound here. I have magnesium chloride, for example. Okay, so I have 1 atom of magnesium and I have 2 atoms of chlorine. If I look at the periodic table, my magnesium is in group 2. So its oxidation number will tend to be a +2. Chlorine is in group 17, so it has 7 valence electrons. It's going to want to gain 1 to make 8, so each of these two chlorines has a -1 oxidation number. Now, this is what I can do. My +2 plus a -1 plus a -1 totals up to 0. And that's going to hold true for any compound. Let's try another one. Let's say that I have lithium and bromine. Okay, so my lithium and my bromine each have an oxidation number. Lithium is in group 1. So group 1's oxidation number as a metal tends to be +1 because it has 1 valence electron that it likes to give away. Bromine, again, is in group 17, so it has 7 valence electrons. It likes to gain 1 to become a -1 oxidation number. So again, I have a +1 plus a -1, and that totals up to 0. Now that's actually not too bad, but what this also does is it allows us to find the oxidation number of those transition metals. Now remember, we hadn't been finding anything out with those transition metals before simply because their valence electrons sometimes change. So let's take a look at an example of one here. I can have CuBr, copper bromide. So I can have this and this. Now, I can't predict just yet the oxidation number of copper, but I can of bromine. Bromine's oxidation number, we know from the last example I just did, is a -1. And the other thing that we know is whatever copper is plus the -1 has to total up to be 0. So that tells me that this has to be a +1, and that in fact is what copper's oxidation number is. Now, like I said, copper can change its oxidation number. So let's take a look at another example here. Copper oxide. Okay, yet again I have my copper and my oxygen. Now, just like before, I can't predict copper just yet, but if I take a look at oxygen, it's in group 16. Group 16 has 6 valence electrons. They are nonmetal, so they want to gain 2 to get to 8. So oxygen's oxidation number is a -2. So again, we know that whatever copper is plus a -2 has to total up to be 0, and so in this case, copper has to be a +2. So based on that, you can actually assign oxidation numbers for things either individually or whether they are in a compound. Now, when we write our oxidation numbers, and we've been doing this already, the superscripts are placed to the right of the atomic symbol, and they indicate both the magnitude, in other words, how many electrons it's either willing to gain or lose, and the sign of the charge it would form if it gained or lost. That's what the oxidation number is. So the example for in your notes would be something like calcium, which oxidation number is +2 because it's in group 2. Now, in general, with ionic compounds, if I have a positive subscript, the atom has lost an electron, and if I have a negative superscript, the atom has gained an electron. And in this case, it could be either they already have or that is what they like to do. So that's ionic bonds and oxidation numbers. We can also assign oxidation numbers to things that are covalently bonded. So, for instance, let's review again just like what we did with ionic bonding. Covalent bonds is when we share electrons, And remember that a covalent compound has a chemical compound that is made up of covalently bonded atoms. So let's take a look at the composition. They are made from elements at the right-hand side of the periodic table. So these are all nonmetals. And remember, the nonmetals have 6, 7, or 8 electrons that are held very tightly. Now, unlike in ionic compounds, when two nonmetals come together, neither one of them is willing to give up its electrons. So what they do is they have to share them in order to become stable with each other. And when they share, they become stable, and they are now held together because both of the nuclei involved in that bond are attracted to those shared electrons. They keep in very close contact with each other. So let's relate this to oxidation number. The number of electrons an atom is willing to share is called its oxidation number. Now with covalent compounds, we're just assigning the number first. The sign, we have to look at what is in the compound. So for nonmetals, we have to kind of see it in the context of a compound in order to assign an oxidation number. If it's in a covalent compound, the sign is actually assigned based on its position on the periodic table. If it's an element further to the left, it is positive. If it is to the right, it is then negative. So let's take a look at a couple of examples here. And I need to change my ink color quickly so you can actually see it. There we go. Okay, we're going to do two compounds involving oxygen, just as an example. So we are going to have hydrogen and oxygen, water. You guys are familiar with that. All right, so let's assign our oxidation numbers. All right, hydrogen, if we think of the Lewis dot structures, okay, this is what it would look like. We actually have that sharing here and that sharing here. So if we look at the oxidation numbers, okay, oxygen is willing to share 2 electrons. Each of the hydrogens is willing to share 1. Now we have to put the signs there. If you look at the periodic table, the element that's further to the left is hydrogen, so it gets its positive sign. Oxygen is further to the left, so it gets its negative sign. Now, notice, if I still total them up, it still totals up to 0. Now, let's take a look at a different one. We're going to combine oxygen and fluorine. Okay, oxygen is still willing to share its 2 valence electrons, and fluorine can only share that 1. Remember, these here, and I think I forgot to mention this in the last one, they are what we call paired electrons. They don't want to share anymore. It's only these single guys that we actually want to share. Now, if we look at the periodic table, oxygen is further to the left. So in this case, it would actually get assigned the positive oxidation number, whereas fluorine would get assigned the negative oxidation number. And if you do the Lewis dot structures, you will actually see that I would have 2 of them. So I have a positive 2 plus a negative 1 plus a negative 1, and that totals up to 0 again. All right, writing the superscripts with our covalent compounds is exactly the same way as we do it with our ionics. The superscripts are placed to the right of the atomic symbol to indicate the oxidation number. Just like that with oxygen. Now, let's look at the sign. The sign doesn't tell how many it's willing to gain or lose or even share. That's the number itself. The sign simply talks about its position on the periodic table. If it's positive, it's more to the left, and if it's negative, it's more to the right. Now, in our next lesson, what we're going to do is we're going to learn how to use these oxidation numbers to actually write our chemical formulas.